All right, my name is Tomasz Jańczuk. I'm working for Microsoft, where I'm currently focusing on making sure that Windows is a great hosting platform for Node.js. So I'm working on a couple of projects related to Node.js on Windows. If you are interested about that topic, I'll be available after this talk to talk about it. So feel free to get me and we can go there. This talk is about something entirely different. This is about high-density server-side JavaScript, which is pretty much about how to do more with less. So let's get started. So let's say you have just developed a web application, something that most likely has happened to most of us. And let's have a look at that application, actually. So this is an application written in server-side JavaScript. And it's a simple web chat app. So nothing unusual. Basically, you can hit an HTTP endpoint. That endpoint will serve you an HTML page with a bunch of client-side JavaScript that does HTTP long polling against REST endpoints exposed by the same backend hosted in that server-side JavaScript application. The one interesting thing about that app is that it falls into a category of what I call a lightweight web application. And what I mean by that, there is a class of applications that are using very few resources, both in terms of CPU, memory, networking, and possibly disk usage. So the next question you're facing after you have developed such an application is, where do I host it? And there is a number of choices today on the marketplace, varying in the level of functionality and price. But bottom line, what it boils down to, and don't hold me to that number, but €5 will probably buy you a reasonably decent shared hosting plan today. My claim is that €5 is way too much to ask in terms of hosting a lightweight web application. Hosting such apps should be much less expensive. So the question is there anything we can do about it to make them less expensive to run? And during this talk, I'd like to have a look at ways we can help hosting companies lower their costs of running such apps and therefore potentially provide them with an incentive to reduce the pricing of the shared hosting plans. So after you deploy your application to any of the shared hosting providers, it will probably end up running in a place like this. So there is a data center with a large number of machines. Your app is running on one of them, probably alongside a number of other applications, possibly applications written by your competitors. And this is pretty much what you are paying the €5 for. The breakdown of the cost of operating a data center, it falls into three categories. There is the cost of buying the hardware. There is the cost of electricity and maintenance, and there is the cost of electricity is mostly actually cooling the data center, and there is the cost of maintenance. And these categories are roughly 33% each. So the key takeaway from this is if we can reduce the number of machines that are necessary to run a certain number of web applications, we can pretty much proportionally reduce the overall cost of running a data center, and therefore provide an incentive to hosting companies to reduce the pricing of the shared hosting plan. So the typical breakdown of the plans that shared hosting companies offer falls into three categories. You can go and get yourself a dedicated piece of hardware that will cost you most, let's say €200 a month. Then you can go and get a virtual machine running on a piece of hardware. That virtual machine will be running alongside virtual machines owned by others who purchased computing power from that hosting company. Virtual machine provides a good level of isolation between these execution environments. Typically, these hosting plans manifest themselves as the so-called root access to the system, because effectively you are an administrator of that virtual machine, but it is still not a physical box, it's just a slice of that physical box. And the last class of shared hosting plans offered today revolves around process-level isolation. So typically you'll basically have a username created on a system, and you will be able to host your application as part of that username. So most modern operating systems offer kind of user-level isolation within the operating system, where you can control access to resources, meter access to resources at the level of a process that is running within the credentials of a particular user registered with that system. And this is perhaps the densest you can get in terms of application density in case of the most shared hosting plans today. So this is what you're paying the €5 for on a monthly basis. There are two things you really care about when you choose your shared hosting provider. One is isolation of your application. You really want to make sure that your app, when it is deployed to that data center, is not affected by what other applications are doing. You don't want other applications running on the same physical machine as yours to, for example, take away all CPU capacity from your application or affect how much networking you can do. The second aspect, so isolation is one. The second aspect is resource consumption. You really want to make sure that what you are paying for really guarantees you a certain level of access to memory, CPU, networking, and disk. And you really want to make sure that you're paying your fair share of the resources in proportion to what all the applications are consuming on that box. So in case of the class of applications I'm talking about here, the lightweight web applications, as I said before, CPU usage, networking, and disk is probably not the factor that bounds the number of applications that can be running on one box. I think in case of these apps today, it will be the memory. Simply because at the process level isolation, a single process has a certain weight behind it, and you can only run a certain number of processes on a single physical machine, and regardless of the operating system you are using. So let's have a look at what exactly does it mean to run at the process scope. Let's come back to our chat app. I'll just start an instance again. Let's just make sure it is running. Yep. So now let's have a look at the resource consumption of that process. So first of all, you'll notice that CPU usage is pretty much negligible. All CPU usage is actually coming from other processes running on that machine. My lightweight web applications are sitting there, doing nothing, waiting for a message from the client. So this is to be expected. Let's have a look at the memory consumption. So this is my process. There are many ways you can measure memory consumption of a process. There are many different metrics. The one that is most relevant in the context of this discussion, I think, is what on Windows is called private working set. So this is the number of bytes that is dedicated to the exclusive use of that process. So it is not shared between processes. It, for example, doesn't belong to any shared library that is shared across processes. And a subset of those bytes that actually resides in physical memory at that time. So this is not something that is paged out or swapped out to disk. It is something that has to reside in physical memory in order for that application to function correctly. So that number would represent what chunk of the physical memory resource is that particular process using, and therefore how many of these processes could you run at maximum on a system with a given amount of physical memory. So in case of the process we are running here, this is 2.6 megabytes right now. So I'll just take note of that number, and we'll use it in a moment. So process level, isolation, memory. And what you're paying for that level of isolation is €5. So naturally the question is, can we do better? And given that I'm only 10 minutes into this presentation, you can expect that the answer is, I hope so. So how about trying to use threads in order to isolate applications? Most modern operating system provides primitives that help write applications that are isolated at the process scope. You can, for example, put limits on the number of handles a process can create. You can put limits on the amount of memory a process can consume. At the thread level, the number of resources you can constrain or control at the level of the operating system from the outside of the process is very limited. For example, threads are free to access memory within the process. There is no native mechanism within any of the operating system that would prevent one thread from accessing memory that another thread has allocated within the same process. And this is where the difference between native applications and managed applications becomes important. So whenever you're writing an application that you really don't know anything about, it could be written in C++ and use the full functionality offered by an operating system, there is really no way to reason about resource consumption at the sub-process level. There is no way to constrain resources on a per-thread level when that thread is running within that app. What managed execution environments like server-side JavaScript provide us is a layer that separates the operating system from the application code, a hosting layer. In case of Node.js, it is actually the node code, which consists of the V8 JavaScript engine plus the node-specific functionality, the event loop and all the native modules. So it is up to that layer to expose certain primitives to the application to use. If that layer chooses to allow the application to spawn new processes, it's a certain decision that is made at the hosting layer, not the operating system layer. So that layer could effectively provide a constrained set of primitives to the application such that it is easy and actually possible to control resource consumption and limit resource consumption at a finer grain than the process. So in theory, you could run multiple applications within a single process and use the hosting layer to provide both isolation and resource metering between these applications. So a solution that uses hosting layer around a JavaScript V8 engine could look like this. We would have one process that is running multiple threads. Each thread would be running a different application, a JavaScript application. These applications theoretically can compete for access to operating system resources, and it is up to the hosting layer to ensure fair access to resources as well as isolation between these contexts. So JavaScript, the V8 engine, provides a few key concepts that help realize that possibility. So first of all, there is a concept of a V8 isolate. An isolate allows you to create a standalone instance of a JavaScript engine within a process, and you can have multiple of those. What standalone means in this case is that each instance is completely isolated from each other in terms of the resources, the memory resources it uses. It has its own heap, it has its own garbage collector. If you dispose of one V8 isolate within a process, it doesn't affect the other isolates. So as far as I understand, V8 isolates have been meant to support concurrent execution of multiple JavaScript programs within a single process on different threads. A second concept that is not shown here, and I'll go into that later, is a V8 context. V8 context provides the kind of data environment within which a JavaScript application executes. Specifically, in case of JavaScript, it controls the global object that is available to the application code when it runs. So you can have multiple V8 contexts and multiple isolates. When you run JavaScript code, you have to choose one isolate and one V8 context that that application will be running in. In this case, the reason I didn't show a context is because there is kind of one-to-one relationship between isolate and a context. So for each isolate I create only one context and execute the JavaScript application within that context. So let's have a look at how that looks like. So the denser prototype, which is that little hosting layer that I've created for the purpose of this demo, allows you to actually start multiple apps inside of a single process. So I can start 3 web chat applications in this case. And each of these apps is, again, running on its own thread and using its own V8 isolate. So the data of these apps is completely isolated. In terms of access to the CPU, it is actually the operating system that ensures fair access to the CPU because thread scheduling happens in the operating system level. So let's just test that hypothesis that these apps are actually isolated. So I'll pick the first one. So this is chat 1, and I'll take the second one. And this is the chat 2. So you can do chatting in this window, it doesn't affect the chat in the other window. So at the level of the data that these chat rooms exchange, they are isolated. Now in terms of resource consumption, one thing that the hosting layer that I've implemented here does is also provide metering of resource consumption on a per program basis. So what it does, it basically shows you CPU usage, network usage, and memory usage on a per program basis. So you'll notice that this particular web chat instance has used that many CPU cycles so far. It exchanges a certain number of bytes, and that number will increase as you type something. Number of HTTP requests, and also memory usage. So memory usage refers to the memory allocations within the heap maintained by the V8 isolate that application is running in. One thing to notice is that these numbers are different from the second web chat that I have running here. So this is, let's say, 34 kilobytes exchanged. This is 38 kilobytes exchanged. So you've got metering and resource control at the program level, and these programs are running within the same process on different threads. So this is great. This demonstrates that at that level we can actually measure resources and isolate applications at the sub-process level. Now let's see how heavyweight it is to run many of those applications. So I will write 50 of them in a single process. Now let's have a look at the memory footprint of this. 70 megabytes. So I'll go back to Excel, thread, 70 megabytes by 50 programs. So it is 1.4 megabyte per program. Now, if you assume that the shared hosting plan would be proportional to the memory consumption of that application, that shared hosting plan would cost less than €3. So basically what I have shown right now is that from the perspective of the data center, the hosting provider can now run the same number of applications on less hardware. So this is that grayed out section of the hardware at the end of the rack space there. Given that there are fewer machines used to run the same number of apps, theoretically the cost of the shared hosting goes down, and it can be reflected in the price of the shared hosting plan, which is now around €3. Can we do better than that? Is there any way we can reduce the price even further? So let's see if there is a way we can actually share a single thread among several applications running on the system in a way that still provides the guarantees that we can isolate data between applications and control resource consumption for each application. And this is where the V8 context comes in. In this solution, I'm going to use a single thread in the process, a single V8 isolate, which means that all the applications running within that process will use the same heap, the same garbage collector. However, I will use a different V8 context for each of these apps. This is actually the model that Node.js is using today. However, to my knowledge, Node has not been started off with the intent to actually provide the level of isolation that allows you to run competing applications within the same process. You can spawn multiple contexts inside of Node using the VM module, but the code executing in this context is kind of by default assumed to execute within the same kind of trust boundary. It can belong to the same tenant in the context of shared hosting. So why is that? There are actually two challenges with this model. One is the most evil program you can write is this, basically while true. This program will take the CPU and prevent other programs that attempt to run on the same thread from executing. At the operating system level, the operating system will, when it sees an infinite loop like that, it will actually at some point preempt that thread and give the CPU to another thread that is open on that system. But remember that in this particular case, we are running multiple JavaScript applications that potentially compete with each other on a single thread. So if one of those applications has code like that, it will basically hold up to the CPU infinitely from the perspective of sharing it with other JavaScript applications. So this is not to say it is not impossible to prevent this from happening. Remember that when you run code like this in JavaScript, what happens at the JavaScript engine layer, that code gets compiled into some form of assembly code. And it is not, theoretically not impossible to inject checks into that generated code that will prevent runaway programs from executing. However, such mechanism does not exist today in any of the JavaScript engines that I know of. Another problem with the context-based approach is limiting memory consumption. So running several applications using different contexts on the same V8 isolate implies that all these apps are allocating memory from the same heap managed by a single instance of the JavaScript engine. So a program like that would effectively result in ever increasing memory allocation. And there is no mechanism in the V8 JavaScript engine today, the kind of native mechanism that allows you to control memory consumption on a per context level. Such functionality can be built in on top of the primitives provided by the V8, but this is not something that my hosting layer currently has. So again, these are two challenges with this approach, none of which is kind of a smoking gun reason not to do it. I think there are ways to address that problem. However, it is not immediately available in either the hosting layer that I've done or the V8 engine. So nevertheless, let's have a look at what's the density that running JavaScript applications at a sub-thread level using V8 context gives us. So I'm now going to run denser using contexts as the isolation boundary between applications. And this time I'm going to raise the bar and run 1,000 of them. Here. All right, so you have 1,000 web chat applications running within a single OS process using a single thread and different V8 contexts that provide isolation of data between these applications. So this is a large number, so let's just make sure that it is still running indeed. Here you go. So let's have a look at the resource consumption again. CPU is pretty much still dormant. Remember, these are lightweight web applications that are not using CPU. They're just sitting there and maintaining a state of readiness to accept user messages. So from that perspective, you are fine. If you look at the process, memory consumption, 150 megabytes. $1,000 processes, 1,000 applications. Oops. So that's 150 kilobytes per application. So this is actually pretty good. Let's see how a shared hosting plan like that would cost if it was to be priced in proportion to memory consumption. 30 cents. So that's better than €5. So with that, I'm actually going to start a little social experiment. So if you have any questions about high-density server-side JavaScript, why don't you look up Twitter, go to this URL, and ask it, and let's see what an unmonitored web chart results with. So, again, if you look at the data center we started off with, we allow the hosting company to share a bunch of extra machines by going sub-process level. The end result is if you turn these cost savings into reduction of the shared hosting plan price, it is around 30 cents, which is a reasonable price to pay, I think, for my little web chat application. So basically, we started off with the notion that €5 is too much to pay for hosting very simple web applications like that. We have shown and demonstrated mechanisms that can be used to lower that price quite dramatically, over 10x. And if you're interested in looking at the source code of the denser host, which is really a very thin wrapper around the JavaScript V8 engine, it is available on GitHub. On the same account, there is also a project called IIS Node that I'm working on kind of during the day at Microsoft that is used to help hosting Node.js applications in IIS. If you have any questions, this is my contact. And with that, let's go back to the questions.
Hi, great presentation. So I have a question about the overhead. So how does the overhead plays into this? How much does the context switching of V8 cost in terms of CPU and memory usage in this? Because we saw dormant processes and the applications weren't used intensively. So did you put this under stress and to verify how it compares with a traditional approach with process isolation?
Yeah, so effectively what this approach is showing that there are certain constant costs of creating a process on an operating system, as well as certain constant cost of creating a thread in an operating system. That if you take that cost and you actually average it out across a large number of applications, it becomes manageably small. So in case of a process, it is basically all the static libraries that you have to load up in order for that process to function. Once you spin multiple threads within a process that actually share the static libraries, that cost averages out nicely. At the thread level, once you create an additional thread, you have to allocate a stack size per each thread, which again, you can average out the cost of that stack memory allocation when you're running multiple apps on a single thread. On top of that, there is the cost of running a single JavaScript engine, which basically allocates its own heap memory to manage memory allocations of the JavaScript program. So whenever you can share the heap across many apps, you can also reduce the average memory consumption of these apps.
By the way, is Andrea here? Get yourself a mic up there.
Hi, question, how is memory usage on Linux? Is it the same like we saw here in Windows, or? Because I would imagine a lot of hosting platforms would use Linux.
I'm sorry, can you repeat? I didn't get that.
So this is tested on Windows, I guess. Have
Yes.
you measured how memory usage is on Linux? Is it the same?
I've done similar experiments on Linux using Node with a second approach, the one in which you run multiple JavaScript applications using context-level isolation. And the results were very, very comparable. So, the differences you could point out between Windows and Linux in this case would really probably revolve around possibly around memory allocations at the process and thread scope. Whenever you're running applications in that quantity and you average out the memory allocations, they really become irrelevant. These differences become really, really minor.
So there is also a third model in which you will have a application, a thread per application, but make the threads share the same V8 instance. So V8 has something called preemption, which allows you to basically say to V8, please switch between these threads every 2 milliseconds or something. And this will first give you a lower memory usage, like in your second model. And at the same time, you will be protected from the while true loops, because it will just preempt between the threads, giving each thread a fair amount of work.
Yes,
Well,
I agree. There are many models I haven't experimented with that are perfectly legitimate. These are just two kind of reference points in the entire space of possible solutions. So definitely, yes, you're right.
No more questions? Thank you.
Thank you.